We have ourselves here an interesting speed and velocity problem, and so let's take a shot at it. So Sarah runs at a rate of 5 meters per second. So let's think about what a rate means in this sense. If Sarah's running at a rate of 5 meters per second, we didn't define a direction. She could be running in, north, east, south, west, whatever. So we can say right here that this is going to be a scalar quantity, or at the very least, it's going to be just referring to the magnitude of a vector. There's no direction involved, and as the magnitude of a vector is a scalar because it eliminates the direction. So number one, find how far she travels in 3 minutes. So we know from the last video that the average velocity, and so we'll say v bar, is going to be equal to the displacement, so delta s, over the change in time. Now, again, we weren't specified a direction. We were just given 5 meters per second. So in this sense, we're only referring to the magnitudes of the velocity vector and the displacement vector. So the way we denote magnitude is we put brackets around the vector. And this may look familiar to if you've ever worked with absolute value. You can also write it with 2 lines on each side, and that's also accepted. But for the rest of the video, I'll stick with 1 bar on each side, or I may just leave it as so and just presume that we're only dealing with the magnitudes here. So what is her velocity? Well, we know her velocity. It's 5 meters per second. So we can say that 5 meters per second is equal to her position. But what is her position? That's what we're trying to figure out. So we don't know exactly what it is. So we'll leave it as delta s for now. And what is her time? Her time is 3 minutes. 3 minutes. So now I picked minutes on purpose to point out an interesting problem that we're going to have right now. On the left we have meters per second, and that second is the important part. And on the right we have 3 minutes. Did I say minutes per second? I meant meters per second. Well, if I said minutes per second, I meant meters per second. If I didn't, I don't know what I'm talking about. Anyway, on the left we have seconds, and on the right we have minutes. And this is a problem because we can't compare seconds to minutes. Oh, well, we can, but we're going to have to do a little bit of math first. So we need to rewrite this in order to say, well, 5 meters per second, because we're going to convert the minutes to seconds, is equal to delta s over 3 minutes. And I don't know if you guys are familiar with the way to convert units, but this is how we'll do it. So we're going to multiply it by, we want to cancel out the minutes, so we put the seconds in our numerator, so we have seconds over our minutes. So the minutes will cancel out. And there's 1 minute, and for every 1 minute, there's 60 seconds. So the minutes are going to cancel out, so we're left with 3 times 60 seconds. So we can say 5 meters per second is equal to our displacement, or rather the magnitude of our displacement, because again we don't have a specified direction, over 180 seconds. And I'll just say s. Now this is simple algebra. We solve for delta s. We say that delta s is equal to 5 meters per second times 180 seconds. And you can see that the seconds cancel out, which is good because displacement is measured in meters, so we want to be left with meters. And it's also a wonderful way to make sure that you did your math right. For example, if we did something wrong and then we ended up with, say, 5 meters per second, or 5 seconds per meter, or something that wasn't just meters left in our units, we would have known something was wrong, because how could you can't measure displacement in anything other than a distance quantity, such as meters, feet, etc. You can't measure displacement in terms of seconds. It doesn't make any sense. So now we have 5 times 180, or 900 meters. So let's look at problem number 2. So Sarah is still running at a rate of 5 meters per second, but this time we want to find how long it takes her to run 5 kilometers. So again, we're setting up the same scenario where we have the velocity. The average velocity is going to be equal to the change in displacement over the change in time. Now, this time, we still know velocity, so we can still say that 5 meters per second is going to be equal to the displacement. But this time, we know the displacement. The displacement is 5 kilometers. But this time, what we don't know time, so we're going to have to leave that as delta t. And just like before when we had the issue with the seconds and the minutes, now we have an issue with meters and kilometers. So we're going to have to rewrite this so that we can work with, we have common terms to work with. So when we write this, we're going to keep it in meters because that's the SI unit. So we have 5 meters per second. It's going to be equal to 5 kilometers. I mean, we need to transform this just into meters, so we say we want kilometers in the denominator to cancel out, meters in the numerator. 1 kilometer is equal to 1,000 meters. And that's still all over delta t. So the kilometers cancel out, and we're left with 5 times 1,000 meters. So that's equal to, so we have 5 meters per second is equal to 5,000 meters divided by our change in time. So now we just have to do a little bit of algebra. So we can say delta t times 5 meters per second is equal to 5,000 meters, and that our change in time is going to be equal to 5,000 meters divided by 5 meters per second. And the 5,000 over 5 is easy. It's just 1,000. But let's take a look at our units. So we have meters divided by meters per second. So we have 1,000 meters divided by meters per second. So the way we can solve this is if we have a fraction in the denominator, we can just flip it up and multiply it by the reciprocal. So we get 1,000 meters times seconds per meter, which may seem like an odd unit to you right now, but you'll see right now the meters will cancel out. So we're left with what we should expect because we're solving for time. So if we were left with any other unit other than seconds or some other unit of time, we would have known that we're doing something wrong. So now we can safely say that Sarah runs the 5 kilometers in 1,000 seconds.